just don't really tell you a lot. Everything is subhedral because the thing's been recrystallised at some point. The bushveld complex is, I'm thinking probably Archean. I don't know the exact age, I think it's 25 or 2600 million from memory. Ish. About that. So it's been recrystallised, and you can see it's got a more of a metamorphic looking texture to it. I won't go into specific minerals. There's a couple of key things, or both the presence and an absence of a couple of minerals in here, which are a bit telling, but I really wanted to talk about the pyroxenes because they've got quite spectacular exsolution textures. And we talk about exsolution in pyroxenes in the lecture. So these things are probably quite high temperature. And remember when we talked about pyroxenes, I'll do a couple of, you think about that, what they call the pyroxene quadrilateral. So elastonite's up the top there, this is diopside, Edinburgh, anstatite's here.
What slide is this? Oh, this is 1066.
Orthopyroxene, so hypocene and so on are along the bottom here. Augite is up the top. I need a different colour. Where's blue?
It's behind your microscope.
Oh, there it is. I should have done the frame in blue. Doesn't matter. And so augite's here. So there's a miscibility gap there. So there's no solid solution, at least at lower temperatures, in this gap here. But at high temperatures there is. So that would be the range of compositions at lower temperature, and I'm thinking, say maybe below 1,000, but above 1,000, you do get pyroxenes that are in the space here. One of those is pigeonite. And if you look back in your notes, you'll see that there's another thing just in here called subcalcic augite. Now they're quite happy at high temperatures, but just like orthoclase feldspar, they will go their separate ways as the rock cools down. And because they're solid, that happens in a solid state, so you get exsolution. So you get a texture just like perthitic texture, where you get the plagioclase inside the orthoclase, but this time it's, in this case here, we've got the hypocene inside augite. Okay, I'll just zoom in on that one a bit. Okay, so that's a clinopyroxene crystal. You've got a twin straight down the centre there. So the host, these bits here are exsolution lamellae of orthopyroxene inside the clino host. So it started out as this subcalcic augite, this particular one. So its bulk composition, the bulk composition of that grain is still there, but internally it's now got that as a host, and it's got exsolution lamellae of this inside it. You combine those two together in the proportions that you see on the screen there, and you end up here. So bulk composition same, but it's separated into phases. If we're lucky, we can see. I don't know whether the camera's going to allow me to do this, but if you keep an eye on it, then you can. As the OPX is changing colour. Okay. Let me just get, where's my pointer?
Little more pinky grey. That's what I'm looking at.
No way.
You see it?
It's like pink and grey.
So that's staying the same. So the augite isn't pleochroic, but
It's
these
like
little
it's
exsolution lamellae are. See how that changed then? It's green there, and it's got the pinkish colour there. That whole grain up there, so this whole grain here is an orthopyroxene. You can see it changing. Whoops, that's just need to
So it
cross
looks
there.
more green when he's moving.
See how pink that is there? So that's changing quite markedly, but that's the whole grain that's changing there. So that's not subcalcic orogenite, that's down here.
So what's the pink?
So the pink's the hyposthene.
Pink's the hyposthene.
Okay. The green, this green that's not pleochroic is the orogenite. Notice that when you turn that there, the hyposthene becomes almost the same colour as the orogenite, but not quite. But this is probably one of the most obvious pleochroic changes in pyroxene that you'll see. These are relatively iron rich. Okay, almost looks like an orange there, doesn't it? But notice that this here is changing as well. The stuff inside here, and so these things will exolve along planes of weakness. So that will be close to one of the cleavage orientations in the pyroxene. You've actually got two separate stages of exsolution in here. All this fine stuff running this way, they're all exsolution of melee as well. So this has undergone probably 2 stages of exsolution. The second one, you can actually see overprints the first one. You can see an overprinting relationship there. We don't need to get this fancy with your description, but I thought I'd point it out. So that's happened at a lower temperature, and accordingly it's finer. And it's overprinting this one here. So it's happened twice in the case of this grain. You've got 2 phases of exsolution. The big one's the early big one's the most obvious one. And what it shows really nicely, and I'll just try and get that back up so it fills a lot more of the screen, is they call that herringbone texture. It resembles it. That's the spine of a fish, and these are the ribs going off at a different angle on either side. Why are they going off at a different angle on either side? Why have they changed orientation? Yeah, it's because that's a twin plane. Remember I said these things will exolve along a plane of weakness, so that'll be one of the cleavage orientations. Remember, a twin is a change in the crystal lattice orientation, so the cleavage changes accordingly. This cleavage orientation here doesn't change, but the second one does. Okay, so that's classic herringbone texture exsolution in what was this subcalcic orogenite. Now, if you look around at the orthopyroxenes in this slide, and there's one right there. Let me just check the pleochroism on that. Oh no, that's the. Oh, actually, you can see the pleochroism much more obvious than that one. This one's get back down there. Stay there. Notice again, the host there is not changing. So this is the same grey. This one hasn't got a twin inside it, but that's not changing. But look at the exsolution of melee changing colour. From there, where they're almost the same colour as the host orogenite, to there.
Jesus.
Okay, so that's actually, that one hasn't got a twin down it, so it doesn't have the herringbone texture. But that's a classic example of exsolution as well. The host orogenite there. Notice it's showing straight extinction and only first order interference colours. Why is that? Remember, orogenite can do that. Remember, the maximum birefringence of orogenite's second order colours, but it'll show you everything down to nothing, depending on the optical orientation and likewise the extinction angle. That'll be Z, gamma's out here somewhere, so they're apparently parallel. We went through that before when we did pyroxene. So remember, clinopyroxenes can show you straight extinction. If you're looking into the optic axial plane, they will show you straight extinction, and they'll be the same grains that have lower birefringence. It's only the higher birefringence grains of clino that show you obvious inclined extinction. Now, in this slide as well, I'll try and find an example down at the eyepiece. Perhaps I'm so busy. You get the same texture in orthopyroxene, so they're exolved as well.
Beautiful.
Get out. Look, away. These ones are a little bit less ordered. So you've got a clinopyroxene grain there, but all this one here, cleavage running through there, that's all orthopyroxene. And it's got exsolution, try that again, exsolution lamellae of clinopyroxene inside it. So here you've got, what we looked at before was augite with hypersthene exsolution lamellae in it. This is just the complete reverse. Okay, notice there's no twinning in this one. Notice in plain light, this time the host is pleochroic, but the exsolution lamellae aren't pleochroic. So this time you've got augite lamellae inside hypersthene. And if you think about that, and because these are quite large lamellae, they're probably making up 10% or more of that grain, and their composition's up here, the host is down here. If you think about the composition of the grain as a whole before it exsolved, it's pigeonite. Okay, so that's exsolved pigeonite. What we looked at before was exsolved subcalcic augite. Okay, you'll hear the textbooks call that inverted pigeonite, which makes absolutely no sense whatsoever to me. It hasn't been turned upside down, it's exsolved. So it's exsolved pigeonite. So this thing had two pyroxenes when they crystallised from the melt, but they weren't augite and hypersthene, they were pigeonite and this subcalcic augite thing. And now they've exsolved, the bulk compositions of each grain is still what it was when they crystallised, but in the solid state within the grain, the two end members have gone their separate ways because they don't like to be with each other when the temperature's lower. Okay. So yeah, classic, you won't see better exsolution textures in pyroxene than what's in that slide. They're fantastic. Okay, I'll let you get back looking at what you're looking at.